Hi, lecture 37B is our last official lecture about Laplace transforms for this course, though I would like to tell you, because they are so useful for engineering, that I hope in the next month or so that I can make a few more videos about Laplace transforms, again because they are so useful. In particular, I'd like to talk about something called the convolution theorem, a pretty complicated topic, helpful certainly for engineers, including my Bethel students. Here in 37B, as I promised but forgot to do in 36B, I'm going to talk about a discontinuous sinusoidal forcing example. We're going to use Mathematica to help us save time in this lecture, to help us solve these things. We'll also talk about something new, something called impulse forcing and delta functions. Now you can see I have the word functions in quotes there. That's because these delta functions, these Dirac Delta functions in fact, are not true functions in the usual sense of the word. They are functions in a new sense of the word, something that mathematicians often call generalized functions. We're not going to do the rigorous approach for that here, but we'll talk about it intuitively. I would highly recommend a book that I'll put a link to in the description below called The Theory of Distributions, a non-technical introduction by Ian Richards and Hee-Kyung Yoon. It's a very, very good book to give you the basic idea of generalized functions. They're called distributions. Very, very helpful book, and I highly recommend it. But we will take an intuitive approach. Again, we'll talk about Mathematica usage as we go. The impulse forcing, these delta functions are useful, for example, in modeling, say, hitting a mass in a spring with a hammer, okay? Where you've got this quick, high force that happens, and you'd like to understand what happens to the mass. All right, so let's move ahead to the content and our examples. So again, as promised from lecture 36B, let's first do a quick example with a discontinuous sinusoidal forcing, and again we'll solve it with Mathematica. Here is our second order first harmonic oscillator IVP. It's undamped. I could have made it damped, but I made it undamped. Y double prime plus 3y, no y prime term, so it's undamped, equals this forcing function u4 of t, that's the unit step function, whose value is 0 until you get to t equals 4, where it jumps up to 1, times cosine of 5 times in parentheses t minus 4. So there's no external forcing for the first 4 units of time here. Then all of a sudden at time 4, it's like a light switch goes on, and you get this forcing function, which this would become 1. You'd have 1 times this, you get a sinusoidal forcing at that point. The initial position is 0, the initial velocity is -2. Let's go ahead and solve it quickly with Laplace transforms. We'll use Mathematica, and I'll show you the answer also in the PowerPoint. So how can you use Mathematica to solve this? You could use dsolve or dsolve value, but we can also use a built-in function called Laplace transform. And in fact, we can even plug the entire differential equation into the first input of the Laplace transform function in Mathematica. There's my differential equation. You do absolutely need the double equal sign there. This is the unit step function that has the jump discontinuity at t equals 4. If I have just a t in there, it would be at t equals 0. By putting a t minus 4 in there, it jumps at t equals 4. Then you put a comma. Then you emphasize the independent variable for this function, y, is t. And the independent variable for the Laplace transform, by convention, is usually called s. When you enter this, it takes the Laplace transform of both sides of the equation, and it uses properties of Laplace transforms like we have done to rewrite it. So if we, for example, get 3 times the Laplace transform of what? This entire thing, Laplace transform yt, t, s, represents what we've written symbolically as cursive L of y. You have 3 times it from this term right there. This part right here, s squared times the Laplace transform minus s times y of 0 minus y prime of 0 is the Laplace transform applied to y double prime, and using how Laplace transforms affect derivatives. We've talked about that before. And on the right side, you take the Laplace transform of this thing, use the shifting on the s-axis property, the t-axis property, you will get this expression right here. We've talked about those properties as well. You should take the time to check this. So that's what happens when you apply the Laplace transform function in Mathematica to the equation. What do we do when we use this now, when we do it by hand? We try to solve for the unknown Laplace transform. That can be done with solve in Mathematica. Solve solves algebra equations. So I'm solving this algebra equation right here for the unknown Laplace transform. I can use the syntax. If I did this without doing the expand and without plugging in these values, it gets really complicated looking, or maybe it doesn't look as what I'd like it to look like. Here's the way it looks in sort of a nice form. It has now solved for that unknown Laplace transform, and it says it equals this. At this point, we've said, hey, we should use partial fractions on this part to break it apart into fractions before I try to apply the inverse Laplace transform. I could, in Mathematica, just apply the inverse Laplace transform right away. That's a built-in function as well. I can plug in that entire expression here, emphasize its independent variable is s, and I'd like the answer to have independent variable t. And this gives me my solution. What's this thing? Heaviside theta? Huh? T minus 4? Well, heaviside theta is just another name for the unit step function. And the t minus 4, just like the other one, has the unit step at time 4 from 0 to 1. That is the answer. That is the same as u sub 4 of t. If we tried using partial fractions, in Mathematica you can do that with a built-in command called apart. We can break this fraction, ignoring the e to the negative 4s, apart into two pieces. And then we could put the e to the negative 4s back in there, using the coefficients 1 over 22 and negative 1 over 22 to get the same answer as before. Okay? You can check these are the same thing as before. And you can check it in terms of the way I'm going to show you on the PowerPoint. You get these extra things like this thing here and this thing here. Those are done so that we can more clearly apply the inverse Laplace transform to something like that, which we know will involve a sine of 3t in this case. That's where this expression comes from. Excuse me, sine of square root of 3t is what I meant to say. If we try applying d solve value to this, here's what the answer looks like if you use also simplify and trig reduce. If you don't use those things, it looks extra complicated. You don't see the unit step function in there. It's in there implicitly. Notice it's written as a piecewise function. This is what it equals when t is less than or equal to 4, and this is what it equals. True, that really means when t is bigger than 4. Technically speaking, the way we've approached the unit step function is this would be the answer when t is greater than or equal to 4, and this would be the answer when t is strictly less than 4, but don't worry about that. It's not a big deal. They are the same functions. Okay? And here's the way I've shown you the answer in the PowerPoint. There are the details. In going from here to here, if you were doing it by hand, you'd want to use the shifting the axis on the t-axis property that we have talked about. That takes this form, the Laplace transform of u sub a of t times f of t minus a equals e to the negative as times capital F of s, where capital F of s is the Laplace transform of little f of t. That's an assumption in the background there. Apply the inverse Laplace transform to this kind of thing, you're going to get this kind of thing. So when you're looking, for example, here, the a is 4. So we get a u4 of t here. We also get a t minus 4 right there. The inverse Laplace transform of this thing without the e to the negative 4s there would be cosine 5t, because 25 is 5 squared. So you get the 5 there. You also have to replace t by t minus 4. The negative 1 over 22 just comes along for the ride. Something similar happens here. Here it's simpler in that last term right there. Okay? So you can double check this. All right, now what about this impulse forcing? Recall from lecture 35B, this general principle that I mentioned a couple B lectures ago. It is often easier to model what you might call almost discontinuous phenomena with actually discontinuous functions. Right? Flipping on a light switch, hitting something with a hammer are not technically truly discontinuous. They're just almost discontinuous. The time scales involved get so small that they are almost discontinuous. But coming up with almost discontinuous functions that model them is complicated. So it's simpler to use actually discontinuous functions, like the unit step function, or like this new delta function we're about to talk about. Yeah, we're going to do this in a new way here, with impulse forcing. What does this mean? This is when a possibly very large force is applied during a very short period of time. It can be used to model, for example, hitting an object with a hammer. Okay? Just a quick external force, and maybe you even do it periodically. Hit the mass with a hammer. Or maybe there's an explosion that happens or something like that. As a first approximation, we might imagine an external force taking on the following type of form with this type of piecewise formula. This is a discontinuous function if I write it like that. G sub A sub delta t as well equals some constant k, some positive constant, say, when little t, time is between a minus delta t and a plus delta t, and 0 otherwise. So imagine, a can be anything. Delta t is something small. A, say, is there. Delta t is some small interval of time. So that this number right there is a minus delta t, and this number right here is a plus delta t. This interval has length 2 times delta t. The forcing function is 0 when t is strictly less than a minus delta t, or when t is strictly bigger than a plus delta t, and a constant value, k, say, when t is between a minus delta t and a plus delta t, and I guess I'm including filled in dots up there, though it's not a big deal whether you include those or not. So there's an actually discontinuous function that we're using to model an almost discontinuous phenomenon. If we're imagining hitting a hammer, hitting that mass with a hammer, maybe delta t is like 10 to the negative 3 or something, and k is some unspecified magnitude. What should k be? It might be nice here, at least in the initial mathematical modeling, to try to normalize this function here so that it integrates to 1. So that the area under this graph, the area of this rectangle, in fact, equals 1. Without worrying about the physics of it, and whether it accurately models something, it might be best in our initial modeling to pretend this integrates to 1. This is going to be related to the concept of impulse, because the integral of the quick impulse forcing is called the impulse. And if I remember correctly, I think it represents the total change in momentum of the object. So we want to choose k to make the area equal to 1. Well, the base is equal to 2 times delta t. Therefore, the height should be 1 over 2 times delta t. Right there. K should be 1 divided by 2 times delta t. That'll make the area of that rectangle equal to 1. This function will integrate to 1 over any interval containing a minus delta t to a plus delta t. If we're going to use this function with differential equations, we better know its Laplace transform, right? It seems like we probably, since the Laplace transform is handy for dealing with discontinuous forcing functions, we probably better know its Laplace transform. Is it difficult to figure out? It's not the easiest thing in the world, but it's not too bad. Assuming a minus delta t is greater than or equal to 0, here's the definition of the Laplace transform. Ga of t is the integral from 0 to infinity of Ga sub delta t of t times e to the negative st dt. The t's go away. This is a function of s. Think of a as fixed. But because this function is 0 except when t is between a minus delta t and a plus delta t, you can simplify this improper integral to a proper integral from a minus delta t to a plus delta t, assuming this is greater than or equal to 0, of the k value, 1 over 2 times delta t times this. Now do the integral. Here are the details. You get this. So you can check this. Hopefully I haven't made a mistake. You know, I do make mistakes. It's possible there's a mistake here, but I think it's right. Yeah, it's kind of complicated. I mean, you can do it. We're going to actually try to use this in our modeling. Boy, the delta t makes it extra complicated. I wonder if the delta t could go away. That's the motivation for what comes next, is we'd like the delta t to go away. In fact, if you think about this expression on the far right carefully, by this expression I mean this one right here. You might, eventually, maybe, if you're lucky, realize it looks like a difference quotient for a derivative, right? Or not so clear? Usually you write derivatives as limits of difference quotients. The black marker's dying on me, it seems here. F prime of x is like a limit as, say, delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. Sometimes you use h instead of delta x here. There's another limit that equals the derivative as well. You could also say the limit is delta x goes to 0 of a slightly different difference quotient, at least assuming your function is nice. This kind of thing represents a slope of a secant line say from here to here. That's what this thing that I circled represents, and then you let delta x goes to 0, go to 0, and the slope of the secant line approaches the slope of the tangent. The second one here represents the slope of another secant line going between x minus delta x to x plus delta x, like that. You still let delta x go to 0. If it's a nice function, it should still approach the slope of the function at the point x if it's a differentiable function. Now you can come up with non-differentiable functions where this limit exists, but this limit doesn't, like the absolute value function when you take x to be 0. So you really want this one in general, but if it's a nice function, this one will work as well. And this is a nice function, technically speaking, of these quantities, s and delta t here. In fact, yeah, this limit of this quantity that I circled here, as delta t goes to 0, is a derivative. It's the derivative of e to the st when t is 0. Think of s as fixed. It's just a constant. Think of it that way. Think about this limit replacing x with 0 and replacing delta x with delta t. It's that derivative. Got that? Think of s as fixed. Replace x with 0, corresponding to the 0 there. Replace delta x with delta t. And you get the same kind of limit. Notice the function is e to the st. This is f of 0 plus delta t. This is f of 0 minus delta t right there. But that derivative, when you want to calculate it, it equals s. Right? Use the chain rule to get this. Plug in t equals 0, e to the 0 is 1. You get s. Therefore, can we say this is true? The Laplace transform of this is this whole thing, including this part. Can we say the Laplace transform of the limit of this is delta t goes to 0? Can I pull that limit sign out? And then take the limit of this whole thing as delta t goes to 0, which would be that thing times this thing, and the s's cancel to give me e to the negative s. Is this valid? It's not valid in the usual sense of the word valid. It's not rigorous math. But it can be made rigorous if you do the theory of generalized functions. Again, I highly recommend this book. Just going to hint at how to make it rigorous, not do it fully here. I mean, if this were true, what would that imply? Assume for the sake of argument that we can do this. Let little delta sub a of t represent the quote-unquote function defined by this limit. In other words, let little delta sub a of t equal infinity if t equals a and 0 otherwise. In that graph that I erased, as delta t goes to 0, 1 over 2 times delta t goes to infinity. The interval gets smaller and smaller, but the area of the rectangle is still got to be 1. The height's got to get higher and higher. It's 2 times delta t is the height. As delta t goes to 0, 1 over 2 times delta t. As delta t goes to 0, it goes to infinity. You can't do that, can you? That's the part that's hand-wavy, non-rigorous. This infinite value is not just any old infinity, though. It's a special infinity. It's getting even weirder. This infinity must be chosen so that the area under this quote-unquote function equals 1? I mean, that would make intuitive sense, right? Because the area under all those rectangles is always 1 no matter what delta t is, as long as delta t is positive. They keep getting higher and higher, but skinnier and skinnier. The area is always 1. So shouldn't we say we want to choose this infinity so that integral is 1? I mean, wait a minute. What? Yes, you heard me right. And in fact, it must also be chosen so that for any other function, h of t defined near t equals a, when you integrate delta sub a of t times h of t, you get h of a. Correspondence here is here h of t is 1, so h of a is also 1. But here you want to get h of a. What? This is not rigorous math. Don't pretend it is, even though we're pretending it's non-rigorous math, but we're pretending we can do it anyway. We're not pretending it's rigorous. We're pretending it's non-rigorous, but we're pretending we can also do it anyway. Oh boy. In particular, did you see that? What's the Laplace transform of this delta function? By definition, it should be the integral from 0 to infinity of this delta function times e to the negative st dt, but that's my h of t. So I better get e to the negative s times a, replace t with a, which I also can write as e to the negative a times s, which is the same as what I hinted at in the previous slide, right? That the Laplace transform of the limit as delta t goes to 0 of the g sub a comma delta t of t we saw was e to the negative as when I did the limit. It's consistent with that. All this hand-wavy pseudo-math, and it indeed is pseudo-math, can indeed be made more rigorous. Such functions technically need to be rigorously defined as so-called generalized functions in the theory of distributions. If you look it up online, generalized functions or theory of distributions, it's essentially the same thing, just different names for the same thing. In a nutshell, if I had to describe what generalized functions are in one sentence, I would say generalized functions are defined via integrals. They're rigorously defined via integrals rather than outputs. And in fact, linear algebra is still needed here. They're actually linear transformations from function spaces to the real numbers. Give me a function like an h of t, map it to its value at a. That defines a function from a function space to the real numbers. In fact, it's a linear transformation. It's called a linear functional, if you want to look that up. I'm serious, linear functional, add the extra al at the end. That's what I'm talking about here. And we're just thinking about it purely in terms of, say, give me a function h of t, it maps to h of a. I don't even have to write the integral symbol, though intuitively I'm imagining it in terms of integrals. This particular generalized function, this little delta sub a of t, is called the Dirac Delta function, which equals infinity at t equals a and 0, otherwise quote-unquote. Oh, so since we know Laplace transform, I suppose that means we can use it for differential equations. Yeah, that's right. We can use it as a forcing function, for example, for a harmonic oscillator. Now, you'd have to do actual experiments to see how meaningful the results seem to be. And like, you know, is it really normalized so the integral equals 1? You'd have to make measurements like the change in momentum when you do hit it with a hammer to make sure you're using the right delta function, or maybe a constant multiple. Maybe you can multiply delta sub a of t by some non-zero constant, like 5 or 10 or something, to make it be the right one and be the right value of infinity. You'd have to do actual experiments. But let's just do the math. Let's solve this second order damped harmonic oscillator, because I got a 2 there in front of the y prime. My forcing function is delta sub 3 of t, which equals 0 before 3, but at time 3 it equals infinity, enough to give it a total impulse of 1, so to speak. At time 0, the initial position was 0, and the initial velocity, the initial position was 1, the initial velocity was 1. Evidently, this is going to affect the solution in some interesting way, perhaps at time 3. Here's what happens if you apply the Laplace transform. I'll show you the details here quick, and then I'll show you the Mathematica. You need to check these details, and you actually get pretty quickly to the answer using properties of Laplace transforms. In the last example, we used the shifting the origin on the t-axis property. To get from here to here, I'm also using, besides that property, I'm also using the shifting the origin on the s-axis property, which says that if the Laplace transform of little f of t equals capital F of s, then the Laplace transform of e to the negative, actually it's e to the positive at times little f of t is capital F of s minus a. That's needed, for example, to go from here to here and from here to here. Completing the square was needed as well. Actually, I'm not. Actually, it's. I'm a little confused here now. Not sure that I did this right. Okay. Yeah, actually, it is used at each spot actually for all three of these. It's simpler to think about with these two examples, like going from here to here. The s plus 1 is like an s minus negative 1. So in using this, the a for that part is negative 1. So e to the at here, when you take the inverse Laplace transform, is e to the negative t. That's why you get the e to the negative t here and here. And in fact, it's why I get the e to the negative something here, though I also have a t minus 3 there because of the shifting the axis on the t-axis property. That comes from the 3 right there in the e to the negative as. And the u3 comes in there as well from the shifting the origin on the t-axis property. So, I mean, that's confusing if you're not up on things, but if you take the time to really check all this, I believe that is all correct. Hopefully I did not make a mistake. Solution is not actually differentiable at t equals 3. You might even say it's not a solution at t equals 3 then, but it's, you know, well, it still models what goes on. Its derivative, the velocity, has a jump discontinuity, and you might say the acceleration is infinite, which makes sense because it's like the force is infinite for a moment in time. Here's the steps for doing it with Mathematica. And notice the Dirac Delta is in here, t minus 3. And then I can do the same steps that I showed you before and get the answer. And Mathematica gives this answer in terms of the imaginary unit I, which is not so nice. You can use complex expand as well as this other stuff to make it as simple as possible without any i's in it. And there it wrote it in terms of unit step instead of Heaviside theta. I don't know why it doesn't use step sometimes and Heaviside theta sometimes. It's the same function either way. If you do graph it, it's pretty interesting. There is y is in blue, that's the position, and v is in red, that's the velocity. So the position initially is a damped harmonic oscillator, but at time 3, you can tell something interesting happens, and it's not differentiable at 3, there's no tangent line there. And the velocity has a jump discontinuity there. Technically speaking, the velocity doesn't exist at t equals 3. There would be an open circle here and an open circle there. So it's like the acceleration is infinite for a moment in time. And the question is, in real life, how well does this model things? You know, in real life, it would be an almost discontinuous kind of thing happening. Here we're using actually discontinuous velocity to model it, because it's simpler than using an almost discontinuous one. And here's what d-solve value produces if you also use simplified trig, reduce, and expand. And I thought, maybe I need to clear y here. If you get output like that, probably you need to clear a variable. Yeah, there we go. And there it goes back to using Heaviside theta. And the sign here is different than what I wrote, I believe, because Mathematica is writing sine of 6 minus 2t there instead of sine of 2t minus 6, and sine is an odd function, so you get a negative sign involved where there wasn't one up here, I believe, when I did it. When I wrote it on the PowerPoint, at least. All right, and I believe that is the end of lecture B here. Yes. Stay tuned for lecture C, more about partial differential equations in Fourier series. Thanks for watching.